Okay, here we are for part 2 of 6.7, and picking up where we left off, we had just finished filling out the chart for question number 5, and so we know what the relationship of all the roots are, what we expect to see in terms of positive real zeros, negative real zeros, and imaginary zeros of the function. Let's take a look now on number 6 at function p of x. And again, we're going to be counting sign changes. So we have to check and make sure that they're in order by the terms are in order by decreasing degree, and then we're going to look for sign changes. Here we have a sign change. Here we have a sign change. Here we have no sign change, and here we have no sign change. All right, that means that we have 2 positive real zeros, or we might have 0 positive real zeros, because remember, we can either have the number of sign changes that we get, or it can be less than that by an even number. The next thing that we need to do is we need to figure out the number of sign changes for p of negative x. So we're going to rewrite this function, substituting in negative x each time we see an x. And then we're going to simplify. Once we've got it simplified, we're going to count sign changes. As we've talked about in class, it's better to write it all out the first time around, then simplify, and work from there on. If we try to do too much in one step, it's very easy to make a mistake, and of course we want to avoid mistakes as often as we possibly can. So we know that negative x to the 6th, it's a positive power, so we're going to end up with a positive x to the 6th, but we have a minus sign out front, so we're going to end up with negative x to the 6th here. Negative x cubed, when we cube negative x, we get negative x cubed. So we're going to end up with minus 4x cubed after we multiply that positive 4 to it. Negative x squared, following order of operations, we're going to end up with x squared times negative 2. So we're going to end up with minus 2x squared. Negative x gives us positive x, and then we have our minus 1 back at the end. We're going to count sign changes here. So no, no, yes, and last of all, yes. So what this means is we have 2 sign changes. So we have either 2 or 0. So we have either 2 or 0 in the positive, and we have either 2 or 0 in the negative, because it can either be the number that we got, in this case 2, or an even number less than that. Let's go ahead and set up the little chart so that we can organize all of this. And remember, we want to have the positive real zeros, the negative real zeros. In fact, let me go ahead and, since we were kind of color coding, we'll go with positive real zeros, negative real zeros, imaginary, and total. Now this time around, we found that we could either have 2 or 0 positives, and we could have either 2 or 0 negatives. So we have 2 possibilities in each of those columns, which means we have a total of 4 different combinations. The highest degree term, our polynomial, is of degree 6, so all of these are going to have a total of 6 possible roots. So the imaginary ones need to make up the difference. So 2 plus 2 plus 2 equals 6, 0 plus 0 plus 0 equals 6, 2 plus 0 plus 4 equals 6, and 0 plus 2 plus 4 equals 6. So if we wrote it all out, we have either 2 or 0 positive real zeros, 2 or 0 negative real zeros, 2 or 4 or 6 imaginary zeros. On the next page of notes, our example changes a little bit. As you saw on the previous page, The instructions said, state the possible number of positive real zeros, negative real zeros, and imaginary zeros of each function. That was for number 5 and number 6. Now on number 7, it says find all of the zeros of f of x. So we need to find the number of positive real zeros. We need to find the number of negative real zeros, just like we did before. But in addition to that, what we need to do is either factor, and once we factor, well, we need to factor the polynomial so that we can determine all of the roots. That's what our ultimate goal is, find all of the zeros of that polynomial. So it's going to take a little bit of work. What I want you to do right now is turn off the video and find the number of positive real zeros and negative real zeros, and then turn it back on, and we'll move on to the next step for this question. So we've determined by checking Descartes' Rule of Signs, looking for sign changes, that we're either going to have 2 or 0 positive real zeros and 1 negative real zero, with the potential of either 0 or 2 imaginary zeros. So now what we're going to do is we're going to use synthetic division and try to come up with the depressed polynomial. Now, to start off with, I'm going to tell you what factor to use. Remember that our format is x minus r, and I'm going to tell you to find using a 0 of negative 1. So remember, x minus r is equal to 0. I want you to find one using x is equal to negative 1. So negative 1 is going to go inside the box, and what that means is we have to, like we did before, make sure that all of the degrees are accounted for. 3, 2, 1, 0. They are. So we're going to write down our coefficients, and they are 1, negative 1, 2, and 4. We're going to use the same rules that we used before for synthetic division, so you shouldn't have any difficulty doing this. And let's talk about what our result is. We have the remainder, we have the constant, we have the x, and we have the x squared term. So we've been able to determine the depressed polynomial. The depressed polynomial that we came up with is x squared minus 2x plus 4. Remainder of 0, so what that tells us is x equals negative 1 is a 0 of this function. Another way of looking at this is if we move that negative 1 over, we have a factor of x plus 1. That's one of the factors. So we're going to do with this depressed polynomial, if we could factor it, we would factor it. But if you look at it for just a minute, it's not really a factorable one. So we're going to use the quadratic formula. And we're going to plug in, remember the coefficient, a is equal to 1, b is equal to negative 2, and c is equal to 4. So we list those out so that we can plug in properly to the quadratic formula, and then solve for the other roots. So I'm just going to label this. This is the depressed polynomial. Hopefully you're not depressed by now after this question. All right, so let's set up the quadratic formula. Okay, so we had to write small so that we could fit it all in on this question, but we ended up using the quadratic formula to find the additional roots. So altogether, when we list all of the all of the zeros for polynomial f of x, we had negative 1 back from the beginning of the problem, and then we have 2 additional roots, 1 plus I root 3 and 1 minus I root 3, and that is the answer to this question. Okay, so looking at this for one more second, we knew that the possibilities were we were going to either have 2 positive real roots and 1 negative real root and no imaginary roots, or the other possibility was from our little chart, 0 positive real roots, 1 negative real root, and 2 imaginary roots, and that's in fact what we ended up having, was this one right here. All right, so let's take a look at number 8 now. And 8 is modeled after 7. So what I would like for you to do is try this on your own. I want you to turn off the video once again and find the number of positive and negative real roots. and make the little chart so that you can determine the appropriate combination, what you should expect to see, the different possibilities, and then turn the video back on. By using Descartes' Rule of Signs, we were able to determine that we're either going to have one of two things happen. Either three positive real zeros with one negative real zero and 0 imaginary zeros for a total of 4 zeros. Or the other possibility is 1 positive real zero, 1 negative real zero, 2 imaginary zeros, again for a total of 4. All right, so what we're going to do now is we're going to use synthetic division to solve. Once again, we know that our format is x minus r for a factor, and I want you to use a 0 of negative 2. That means if we were looking at the factor, it would be x plus 2 equals 0. This is the factor. And this would be the 0. Okay, so that means we're going to put negative 2 inside the box, make sure all the coefficients are there, and set up the synthetic division. Okay, so we ran our synthetic division, and we were able to come up with the depressed polynomial. Now that we've got the depressed polynomial, what we want to do is we want to take that and do another synthetic division with, and I'm going to give you another 0 to try out. I want you to try out a 0 of positive 2. Once we've got that done, and that will end up, if we can decrease that polynomial, we've already decreased it by 1 degree. And we start out with an x to the 4th, now we have an x cubed. If we can decrease it by 1 more degree and end up with an x squared, we can either factor it or we can use the quadratic equation and the quadratic formula, and be able to come up with the remaining roots. So right now we have one root, x is equal to negative 2. I want you to try out another one, x is equal to positive 2. So I'm going to put in positive 2 inside the box, and we are going to pick up where we left off. So we're not going back to the original polynomial, we're using our depressed polynomial. Okay? So what that means is we're going to take a look, make sure that all of the degrees are accounted for. 3, 2, 1, whoops. There we go. 3, 2, 1, and 0. So let's write in those coefficients. We have 1, negative 8, 22, and negative 20. Setting up the synthetic division the way that we've been doing. And you can see that we ended up with a 0 remainder again, so we knew that that one worked. And our other objective was met. We now have a polynomial that's been depressed by 1 more degree that we can now use in the quadratic formula and come up with our other roots. So that's what I want you to do next, is use this with a equal to 1, b equal to negative 6, and c equal 10, and use that in the quadratic formula, and then turn the video back on to check the roots that you've got. Now you already have seen you have 1 negative real root, 1 positive real root, so we know we're looking for 2 imaginary roots with the quadratic formula. Turn the video back on when you find them. Okay, now that we've used the quadratic formula, we've been able to determine the 2 remaining roots, 3 plus I and 3 minus I. So we have a grand total of 4 roots, which we knew we were going to have. One is positive, real, the other one is negative real, and then we have 2 imaginary roots. And let's just read the note down at the bottom of the page. And it says, if a plus bi is a 0 of the polynomial function with real coefficients, then a minus bi is also a 0 of the function. Those are those complex conjugates. If a minus bi is a 0 of the polynomial function with real coefficients, then a plus bi is also a 0 of the function. On the next page, we have examples 9 and 10 to finish out our section 6.7. We want to write a polynomial function of least degree with integer coefficient whose zeros include -5 and 3i. If 3i is a 0, then we know that -3i is also a 0. We're going to use factors to help us out. They already told us what the zeros were, so we know we have an x that's equal to